I'm Joshua Bardwell, and this is episode 7 in my series Blackbox 101, where I teach you how to use Blackbox to troubleshoot and tune your quadcopter. This is a series, builds on each other, and if you haven't watched the earlier ones, please go ahead and check out the playlist down in the video description. Start from the beginning and work your way up to here. And if you jump in the middle, you may wind up more confused than when you started. In this episode, we are going to be talking about the I term. So a PID controller consists of the P, the I, and the D, and we've talked about the P term up till now. And the P term, as we said, tries to reduce error to 0 by sort of pushing on the physical system. Well, it turns out there's a couple things that the P term simply can't deal with. Because the P term is proportional to the magnitude of the error, what that means is that when the error is 0, the P term is also 0. Well, a good way to think about this is it's like if you were driving a car and the car started drifting off the road, so you recenter the car in the lane and then you go, good, you take your hands off the wheel. Done. What's the car going to do? The car is going to drift right out of the lane again, and you're going to, oh, get back in the lane, get back in the lane. Car gets centered in the lane. Good, we're good. You take your hands off the wheel. Anytime error is at 0 or is very close to 0, the magnitude of the P term is very low or is 0, and as a result, the system that was doing exactly what it was being commanded to do will begin to drift. Persistent bias refers to, a good way to think of that is, let's imagine that the CG of your quadcopter is not centered. So if we imagine we've got your quadcopter here, we're looking at it from the side, and let's say that the CG is not quite centered. As you begin to spin up the motors and lift off, what will happen is that the quadcopter will tip backwards because there's more weight on the rear motors than the front motors, and by default all the motors will spin up the same amount. The copter will then begin to pitch back. Now, the P term will attempt to correct this, but because of steady state error, it will not be able to fully correct it. It will keep nudging the quadcopter back to try to correct for the uncommanded motion, the tipping backwards, and it'll just keep happening. Okay? Both of these things are dealt with by the I term. Now, one way to describe what the I term does is to say that if the P term is proportional to the magnitude of the error, the I term is proportional to the magnitude and the duration of the error. In other words, if there is an error that is consistently not being corrected by the P term, the I term will rise in magnitude in proportion to how long that error has been happening and will compensate for it. In short, this means that the I term can compensate for steady state error and persistent bias. Now, when we talked about the P term, we said that the P term, when responding to internally induced error, the P term should be pushing in the direction we want the gyro to be going. The gyro and the P term should be pushing the same direction. And when we're responding to externally induced error, in other words, uncommanded error, the P term should be moving opposite to the gyro. The I term is a little bit harder to figure out what it's supposed to be doing. Let's take an example of a quadcopter, and let's imagine that it has a very high CG. So let's imagine a quadcopter with some kind of a weight, like on a pole way up high above the quadcopter. What's going to happen when that quadcopter banks into a turn? So let's imagine that it's banking into a turn now. It's banked over. Well, what's going to happen is that the quadcopter is going to want to fall into the turn. The high CG is going to make it want to fall this direction. Okay, it's going to want to tip over. This being the plane of the motors, if you will, or the thrust plane. And so then what's going to happen is that the inside motors are going to have to spin faster and the outside motors are going to have to spin slower to counteract that force. And what we'll see with this quadcopter with the high CG is that when the quadcopter is banked to the left, the I term is pushing in opposition of this force. Okay, so the I term is always going to be pushing outside of the turn. If we're turning left, the I term is going to be pushing right. It's going to be opposing the direction that we're turning, and that's normal. That's good. On the other hand, if we imagine a quadcopter now, let's imagine one with a low CG, for example, maybe one with an underslung battery or something like that. In that case, if we're banked into a turn, CG is low, the quadcopter is going to want to sort of pendulum back to level. And here what we're going to see is that the I term is going to be pushing the opposite direction. The I term in this case, if we just follow this all the way around, you see, the I term is now pushing into the turn. So we are banking to the left and the I term is pushing to the left. In this case, the outside motor is going to spin up and the inside motor is going to spin down. So depending on the CG of the copter is going to have a different persistent bias as we go into a turn. If the CG is high, the copter is going to want to fall into the turn. If the CG is low, the copter is going to want to level out. It's going to want to fall out of the turn. And the correct value for the I term will depend on which of those scenarios we've got. So it's not as simple as saying that the I term should always agree with or always oppose the gyro. What we need to do is we need to examine the quadcopter and look at the different states of flight. For example, when we're in forward flight, very often in forward flight, we're going to see that the pitch I term is pitching forward. And the reason for that is if we've got a quadcopter, it's pitched forward and it's flying this way. The rear props are going to be seeing dirty air from the front props. So the front props make all this dirty air, and the rear props get that dirty air, and as a result, the quadcopter has a tendency to pitch back. And because the rear motors are not spinning as fast as they need to be to make the amount of thrust that they need. And what we see is that the pitch I term is very usually pushing forward in a pitch forward movement to counteract that tendency. And what this means is that the rear motors spin faster. Now that's a very common thing. It's very common to see that for most quadcopters, the pitch I term is pitch forward. It means a positive I term in Betaflight. For banking left and right and for the yaw axis, it depends very much on where your CG is. It depends where your CG is also for the pitch axis, but actually not as much as many people seem to think. In my experience, the aerodynamic effect dominates. I've tried moving the CG of many of my copters forward and back and found that it has very little effect on what the pitch I term is doing, that it's almost always the aerodynamic effect that's dominating on the pitch axis rather than CG. On the roll and the yaw axis, there's less influence there. And what you need to do is you need to study your copter's black box logs and see when you're rolling left, is your roll I term positive or negative? And that tells you which way your copter is tending to fall. Is it tending to fall into the turn or tending to fall out of the turn? Now that we've got that little primer out of the way, let's take a look at some actual black box logs and see what it looks like when it's actually in flight. So here I've got a black box log file loaded, and let's just take a quick look at the header so we can see what my PIDs are. This is Betaflight 315. And you can see I'm pretty much at the default PIDs. These aren't exactly the default I gains. They're pretty close though, and the P gain's been tweaked a little, but that shouldn't really affect what we're seeing. So we're basically at a default tune here. Nothing radical. I've set the graph up here with gyro and RC command for the pitch axis up here on top, and the I term down here on the bottom. I feel like having, unlike the P term, where I felt like having them all three on the same axis was useful, here I think having them on separate axes is going to be useful. And the reason for that is that the I term is not going to directly follow the gyro in the same way that the P term did. So it's not going to be helpful to have them both in the exact same, on the exact same graph. We haven't taken off yet. We haven't throttled up yet. The motors are just idling. And we can see that the I term is at 0. There is no persistent bias for the I term to compensate for. There's no error. Nothing's really going on. As we begin to throttle up, and here we can see the throttle goes up and we pitch forward. And notice that as we do that, the I term goes positive. Now, positive I term is pitch forward. It means the I term is pushing the copter to pitch forward. And what that tells you is that the copter is experiencing a tendency to pitch backward that must be overcome. So whenever you see the I term moving in a given direction, that tells you that there is some persistent bias that is forcing making the copter want to go the other direction. By way of example, if you looked if I was driving a car and you looked and I was holding the wheel cocked over to one side, well, if the car is going straight but I'm holding the wheel cocked to one side, then that tells you that the road must be slanted. I'm fighting a persistent bias by holding the wheel cocked to one side. So we see the I term go positive. It tells us that we have a pitch back force that's acting on the copter, and that is that aerodynamic effect that I told you about. Many people think this means that the CG of the copter is too far back, and that could cause this as well. You're absolutely right that that could cause this. If you want to experiment with this, hover your copter and look at the value of the I term. If the I term is positive, it means the copter is wanting to pitch back and the I term is pushing it forward. If the I term is negative, it means that the copter is wanting to pitch forward and the I term is pushing it, is counteracting that by making it push back. And you can play with that. You can play with moving your CG on your copter forwards and backwards and seeing what kind of an effect it has on your I-term. In my experience, moving the CG does not significantly affect the value of the I-term. The I-term in forward flight, not a hover, but forward flight, is always positive on the copters that I've seen, pretty much regardless of where you put the CG. So what that tells me is that the CG is not the dominant factor in causing this pitch back motion that the I-term is opposing. As we begin to fly, we can see that the I-term stays pretty much positive. Now here I'm going to jam the throttle, and as I jam the throttle, notice that the I-term, the magnitude of the I-term rises. And the reason for that is that depending on the speed of the motors, that aerodynamic effect that makes the copter want to pitch backwards can be greater or smaller. So as I move the throttle rapidly, the I-term has to move to compensate for the changing aerodynamic situation. And this is why when you jam and cut the throttle, the nose of the copter may pitch back and pitch forward. The I-term can't move quickly enough to completely compensate for that effect. We can see that as I jam the throttle, the I-term grows. In other words, it is pushing the copter to pitch forward harder. And as I cut the throttle, notice that I cut the throttle, and if we look, let's just put the throttle down here. Oh, that's good. Let's add the throttle right here. Notice that as I cut the throttle, the I-term moves with the throttle. Here's another throttle punch. As we raise the throttle, the I-term rises. And as we cut the throttle, it goes down again. Notice that there's a little bit of a delay here. The I-term bottoms out here, but the throttle bottoms out here. This is what I was looking for in the last one. The last one didn't quite show it as well. But notice that here's where the I-term bottoms out, but here's where the throttle bottoms out. So they're a little bit out of sync. The I-term is lagging a little bit behind the throttle. And that, again, is why you can get the nose pitching down or pitching up when you raise and chop the throttle. Now on the pitch axis, largely what we're going to see is that the I-term is dependent on the throttle. As we move the throttle quickly, the I-term will have to move quickly to handle the new aerodynamic situation. On the pitch axis, also, if we flatten out into a hover, for example, toward the end when I'm landing, perhaps I will flatten out into a hover. Let's see. Yeah, almost. See, as I lower the throttle, I never quite get into a hover, but the slower I'm going and the less I am pitched forward, the lower the magnitude of the I-term is, because that effect of the rear props seeing dirty air from the front props is less pronounced. Let's go ahead now and look at a roll axis. As we begin to take off, notice that the I-term is mostly 0. And it's going to stay 0 until I turn left or right. In general, our copters are pretty well balanced across the roll axis, and there's no aerodynamic effect that creates a left or a right roll or a left or a right yaw, usually. And so what we'll see is that the I-term is going to be close to 0, indicating that there is very little persistent bias on the roll axis. And let's see if I can find something like a turn. Here, as I go into a left turn, even then, notice that as I go into the left turn, the I-term is still pretty close to 0. And what that tells me is that even when the copter is rolled over, there's not a persistent bias. There's not a tendency to fall into or fall out of the turn. And that may indicate that my CG and all the other effects are relatively well centered for the copter. Ideally, this is what we'd like to see. We'd like to see the I-term pretty close to 0 pretty much all the time. The reality is that's not going to happen. But the fact that I turn left here and the copter, the I-term does not become strongly positive or negative, means that the copter is relatively well centered on that axis. Now here, what's happening here, I'm centering back out. Now the I-term goes strongly negative. So the copter is rolling to the right, but it's tending to not roll to the right fast enough, or to roll to the right too fast, and the I-term is trying to oppose that by making it slow down. So here we can see that RC command is positive, but the I-term is negative. It means that the copter is having a tendency to fall into this move, and the I-term is fighting it and making it making it push against that. And here as we center out again, it becomes 0. And now we're going into a right turn. and the I term goes strongly negative again. It'd be interesting to take a look at the video and see what the copter is doing when the I term goes negative here. Yeah, here again, we've got a right turn. RC command is positive, and the roll is negative. So maybe there is, in fact, a tendency to fall into the move, and therefore the I term is fighting that. Do we see it go, again, right turn? I'm doing a lot of right turns. Can I have a left turn? There's a left turn. As we go into the left turn, we do see the I term go positive. Again, it's fighting it. So in as much as we could try to characterize what this copter is doing, we could say that when we're doing these turns, the I term tends to oppose the move. And what that tells us is that the CG is high. The CG is high, or there is some other aerodynamic effect. But on the roll axis, I think the CG is likely to dominate. I could be wrong about that. The copter is tending to fall into the move too fast, and the I term is opposing the move. Now, whether that's good or bad, we don't know. We just know that that's what's happening. If we look at the yaw axis, we can see as we take off that, again, the I term is relatively close to 0, indicating that we don't have any persistent bias on this axis. If you do see that there's a consistent bias, if you do see that there's a consistent non-zero I term on the roll or the yaw axis, it usually means that, like, for example, if you had a prop that was slipping a little or maybe it wasn't making quite as much thrust, then you would see a persistent bias away from that, or making that motor spin up, right? So if you look and you see that the yaw axis is consistently negative, even in straight and level flight, that's indicating that something is making the copter tend to rotate the other direction, and the I term is fighting it. And you're going to want to look for, generally it's something mechanical, but it could be something, in terms of drag, something off-center drag on the copter or something like that, that's making it have to do that. Another thing we want to look for with the I term is that when you're transitioning from left to right or front to back, but we don't often transition from front to back because our copters are usually flying forwards. But when we're transitioning from left to right on either the roll or the yaw axis, we want to see the I term cross the axis at about the same time as the gyro. So in this case, we can see that I'm yawing to the right, and then I center the stick and begin to yaw to the left. And what we would want to see is that the I term changes directions about the same time that the gyro does. Now, it doesn't matter whether the I term is going from high to low or low to high. The correct value for the I term depends on, like we said, whether the CG is high or low or various other factors. But if the I term is positive when we're turning left, then probably the I term should be negative when we're turning right, right? It should flip. And we want to see that the change in sign of the I term roughly matches the change in sign of RC command and the gyro. So what we don't want to see is, we don't want to see RC command and the gyro change from negative to positive, but the I term stays strongly negative and is fighting the change in direction. That'll manifest in a stiff or reluctant feel to the copter's turns. It used to be that we'd see that a lot on the on the yaw axis, but frankly, I think that they've cleaned up the I term logic pretty well, and I'm having trouble finding examples of a misbehaving I term to show you. Well, here's one where I know that it's misbehaving. In this log, we've got an I gain of 10, and that's not enough really to keep the nose steady. And in fact, later in the file, you can see I turn it. Here's in-flight adjustments happening. The I gain goes down to 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And I actually turn both pitch and roll down to 0. So at this point, the I gain is at 0 on pitch and roll. And what we're going to see is that the I term basically just stays 0. And what that manifests as is, if I center the sticks here I've centered the sticks, the copter will drift and the gyro will show some drift. And you can see here I've raised the throttle and corrected it. So we can see here that the I term is just not doing anything. It's very inactive. It's just not doing anything. And if we look at the video, and you can see the video in my PID tuning masterclass, there's a video dealing with the I term where you can see this exact flight. I haven't taken the trouble to sync the video up here, but you can watch that video if you like. I center the sticks and the copter just rolls to the left and pitches forward. It's a little difficult to see here looking at the traces because they're so slow, and it's an example of why it is important to look at the video as well as the black box logs. I want to take a minute to look at specifically what the I term does during a flip or a roll, because during extreme movements like this is the time when I term windup can happen, and Betaflight has some features built in to prevent that. If we look here, this is a roll, and we're doing a left roll. As we go into the roll, notice that the I term becomes negative. It's the same direction as RC command and the gyro are moving. What that tells us is that the copter is not rotating as fast as it's being commanded to rotate, and the I term is trying to compensate for that by speeding up the move. They're pushing the same direction, it's trying to speed up the move. But what we can see here is that the I term gets capped. So you can see where it goes flat here. It's being capped, and that's what happens during extreme moves. It prevents the I term from growing past a certain magnitude. If you look at some older versions of Betaflight, you'll see actually kind of a shark tooth looking shape where the I term is being reset to 0. And I suppose they're not doing that anymore. I suppose they're capping it during extreme moves. I'm not actually 100% sure what the logic is that they're using. But the I term is not allowed to grow past a certain value during the flip or roll. Notice, by the way, also that RC command levels off here, right? And that is a coincidence. I'm pretty sure that that's where it caps. I'm not sure if it's, usually it's based on the rotational rate. Once the rotational rate passes a certain amount, the I term is capped and is prevented from getting any higher. And the thinking there is that if the copter is doing a move where it's spinning really fast, chances are that the I term just can't keep up. It can't change values fast enough to keep up with the changing situation that the copter is in, and it should basically just take a back seat until we're done with the move. Notice that that's not a hard cap. See, if we look right here, we can see that the I term has gone negative, and it's gone more negative than it was during that flip or roll. So that's not just an artifact of the display or anything. It's actually being capped at this value. Okay, so that's the I term, and I'm sorry to say that unlike the P term, where there's a little bit of troubleshooting and logic we can sort of bite our teeth into, the I term is a little bit boring. The I term tells you what's happening with the copter, but as far as bad behavior goes, frankly, the logic around the I term in modern flight control software is so good that it seldom misbehaves. Examples of misbehavior could be things like I term windup. In I term windup, the I term will accrue a very large value during an extreme move like a flip or roll, and then at the end of the flip or roll there will be some bounce back. And I don't have an example of that to show you because I haven't seen, I can't remember the last time I saw I term windup making a problem. They've sort of fixed it. Another thing that you can do with the I term is you can look for roll or yaw to be strongly non-zero during neutral forward flight. In other words, you're not turning left or right, you're just flying straight. And if roll or yaw is strongly non-zero, the roll or yaw I term, that indicates that the copter, it may indicate that you have a bad prop or a bad motor. For example, if you imagine that the two left-hand motors had bad bearings and were dragging, the copter would tend to roll to the left and the I term would push to the right, and it would just be constantly pushing to the right, except when maybe you did a sharp turn. But during forward flight, it would always be pushing to the right. And that would tell you that something was making the copter want to roll to the left, right? And then you could try and figure out what that is. Anytime you've got a non-zero I term, you are theoretically limiting the max performance of the copter. And the reason for that is, let's go to the example of forward flight. In forward flight, the rear props get dirty air from the front props, and therefore they have to spin faster to make the same amount of thrust to keep the copter from pitching forward or back. Since the rear props have to spin faster than the front props, another way to put that is that the front props have to spin slower than the rear props, which means that if you go to full throttle, the rear props will achieve full throttle, and the front props will have to achieve 85% throttle, or whatever the right proportion is to compensate for the dirty air that is getting to the back props. And what that means is that the copter will have slightly less thrust or speed than it otherwise would. Maybe you should make it heavier so it'll go faster. So anytime you've got a non-zero I term, the copter's top-end performance is being restricted. Does that matter? Well, sometimes. Some of you guys out there are racers who are at full throttle on every straightaway. And if that's you, then finding a way to make the magnitude of the I term smaller, which means that the motors are spinning closer to the same speed, will give you slightly more top end. But really, I think the roll and the yaw axis are where you want to be looking for non-zero I-terms in neutral flight, because that usually indicates something mechanical wrong with the copter that's making the copter want to yaw or roll in a given direction. And that really should never be happening. The other thing to look for is look for the I-term staying on one side of the line when you do a left to right or right to left move. So if you're doing a left turn and the I-term is positive, and then you shift from a left turn to a right turn, then you want to see the I-term change signs from positive to negative or negative to positive at about the same time that you make that move. You do not want to see the I-term sticking on one side of the line, so the gyro crosses over and RC command crosses over, but the I-term stays where it was. That indicates excess I gain, and it means that you need to turn your I gain down. You'll probably feel that as well, but you may not know exactly what it is. Well, that's going to wrap this one up, and I have to say I feel a tiny bit guilty. Some of you are probably going to crucify me in the comments. Take it easy. Come on now. I feel a tiny bit guilty because I've told you about these things that the I-term can do bad, but I haven't really showed you examples of them. And the reason for that is I can't remember the last time I saw an example of these things. I'm remembering seeing these things years ago, a year ago anyway, and they used to happen all the time, and they just don't happen as much anymore. Even when I was playing with my PIDs for the PID tuning masterclass, trying to make the copter do bad things, even raising the gains to very extreme levels just didn't make anything extraordinarily bad jump out of the black box logs. And that's a testament, I suppose, to the coders who've made this firmware work so darn good. There you go, though. There's your look at the I-term. Hope it was educational. Hope you learned something. And as always, happy flying.